And then from using this picture, we can see that the different topological term will give a different SPD phase. But what do you mean by different topological term? Well, this is a very fancy mathematical notation. It's a home of pi d plus 1g to z. And this mathematical object basically describes different topological term. The reason this fancy is that the different topological term is a map. You know, the so-called different topological term means it's a linear map that map the different map to the integer. So this is really a little bit awkward way to say. So this pi d1 describe different class of map from space-time to G. And topological term is a map, it's a linear map that map this map to integer. And but actually it's just so the physics is very simple, and it's just physics usually don't say this awkward way. You just say, okay, the topological term this integer coefficient, and that's it. And so this different choice integer coefficient corresponds to different topological term. But the mathematicians say that this different choice integer coefficient means choose different element of this home of pi g z. You know? And the reason I write this general notation is that using this nonlinear sigma model, this result we get. We claim that if you do this way, we say SPD states are described by this kind of mathematical object. Okay. And this result turns out to be wrong. Actually, it's at least not always correct. Sometimes it's really wrong. The reason is that this result is wrong because of following. Here we are talking about the fixed point where lambda go to infinity. When lambda go to infinity, you can see that there's nothing constrain the derivative of G. So therefore, the derivative of the field can be infinity. But infinite derivative is a little bit strange. You know what do you mean by infinite derivative? So here that we have to consider the lattice, because all the field theory have ultraviolet regulation, have the cutoff. So we have to we have to really bring in the cutoff. So put our nonlinear sigma model on the lattice. So in this case, when you put the nonlinear sigma model on the lattice, when the lambda goes to infinity, that means the field on the different lattice point, even on the neighboring lattice point, can fluctuate independently and randomly. There's no relation. There's no sense that the field at this lattice point and the field at the neighboring lattice point, they are kind of close to each other. They're totally random. So that means there's no continuum limit. There's no way to, using lattice model, to get the continuum limit, to get the field theory. So actually, there's no field theory in this limit. And if there's no continuum limit, we don't have this homotopy theory, because homotopy theory is a continuous map. So we require this field to be continuous. But actually, the field is not continuous in lambda go to infinite limit. And so we don't have a homotopy theory. We don't have a pi d plus 1. We just don't have that. There's no there's no sense of continual field theory. So we are talking about nonsense here, actually. As you can see, we seem to have a very nice theory, nice story, but it's nonsense. It's really we don't have all this. Just we don't have this at all. And then it's back. So then say, okay, then we have even simpler result, because there's no continuous field, there's nothing there, there's no topological term, and all the fixed point theory should be the same, because we don't have 2 pi topological term. So maybe we only have one kind of fixed point theory. So maybe there's no non-trivial SPD state, only one product state. That's all we have. So this after realize this, it looks like maybe that's it. We don't have SPD states. And so the issue really became that when the space-time became a lattice, when you put the theory on the lattice, when you don't have a notion of a continuous field, can we still define topological term? If we cannot define topological term, then then we don't have SPD states. If we can still define topological term, then we will have SPD states. So it's really a question that can we define this notion of 2-pi quantized topological term even when the space-time is a discrete lattice, and so the field don't have a sense of continuation. And so it turns out the answer to this question is yes. Even on the space-time lattice, we can still define this topological term. But however, the mathematical theory for such topological term is no longer homotopy theory. It's not pi, that's homotopy theory, but became another theory called homology or cohomology theory. So there's a cohomology theory which is defined on the simplex or complex, and which do not require this continuous notion of continuous manifold. And those theory allow us to define topological term. So actually, in mathematics, this homotopy theory and the homology theory are kind of have some relation. And so this generalization from homotopy theory to homology theory is actually a generalization from continuous spacetime to lattice spacetime. That's also play. So this is really it's a key here. Here I just want to make a comment is that we know that this topological insulator for the free fermions can be classified by so-called K theory. And the K theory is something like homotopy theory. So it uses a sense of a continuation, something continuous. So K theory belongs to homotopy theory. So in my mind, it belongs to this analysis. They have a manifold continuum, this kind of thing. And so therefore, the classification of a free fermion topological insulator actually belong to this kind of analysis. And that kind of topology, and the topology associated with the continuation. But however, for SPD states, we also have topology, but this topology is very different topology. It's topology of homology or cohomology, that kind of topology. And this kind of topology actually is algebra, do not require anything continuous. So so these SPD states and the topology order I talked about yesterday all belong to the second topology. So basically, unfortunately, the name, this term topology is an overused name. It's really have very, very different meaning. There's a classical topology, which is like a homotopy or case theory, associated with the continuation, continuous map. That's kind of classical topology. And the classical topology, and so in this non-linear model here, I use so-called classical topology. And the topology insulator also involved this classical topology. But however, the topological order and SPD states, that's what I'm going to describe in a moment, that they do not belong to the classical topology. They belong to so-called, let me call it quantum topology. This is actually algebra. It's not really topology, really algebra. And so this quantum topology is a key to understand the quantum system. Yes?
So a nice question. So in the condensed matter system, I mean, to have a discrete time seems to be hard, right?
That's right.
And so is it possible that you just keep the time continuous and just discretize the space? Is there any implication on what you're going to say?
Okay. So here, actually, I'm using the imaginary time. So I think that's maybe okay. And in a sense, in the imaginary time, we just think as decay to ground states. So even for discrete time or continuous time, they all decay to ground states. And so we don't have too much trouble or difference for discrete time and continuous time. But for the real time, I think that there is a big issue here. But here, when you consider this, if you're careful, you will see that. So there's no I here, and there's I here. So this is really the imaginary time passing rule. So the dynamical term is real. So when you do this action amplitude this one is suppressed. But the topological term is a purely imaginary. This is very important. Actually, in the action, in the maritime action, there's a term which is real, which is dynamical, like a potential term. And there's a term which is purely imaginary. That we call barrier phase term or topological term. The topological term always in the purely term. And because of this, and in the maritime, this discretizing in maritime and is okay. So next I will try to define this topological term in a space-time lattice. Can we do how to do that? So in order to do that, let's try to go to formulate a path integral in space-time lattice. Let's do that in a very simple case, like 0 plus 1 dimension. This 1 dimension is just a time direction. And in the Hamiltonian formulation, the partition function just trace of the e to the minus beta h as a partition function in the imaginary time. And we can write this trace. We can divide this e to the beta h as e to the delta beta h and multiply this operator many times to build the total data. I should have minus sign here. I forgot. There should be minus delta beta h. Okay, so this new one basic matrix element of e to the minus delta beta h, and this G0, G1 just an index which live on the vertex here. That's a one-dimensional time. Okay, so then we can just write this trace as a product of many this matrix, and then we take so here the way I write this is matrix element. So this is a matrix element. So we multiply those matrix element, summing over the index. That means like taking the trace, and so we can write the partition function this way. But here I will do something a little bit fancy. First, I want to point out that this matrix is not symmetric. Means this exchange this index give us different value. Okay. But here we want to have the geometrical picture of this path integral. Okay. So basically we have a space-time, we have a time direction, we have a triangulation, we have a lot of segment. So therefore each term, each new relate to each segment. And this G0, G1 just an index live on the vertex here. So that is a geometrical picture for this path integral. But however, we have to say which index is go to first, which index go to second. We have to make a convention because this one is not symmetric. So therefore, we have to put arrow to each cell, so that we can say that the one with no incoming arrow going to first, the one with one incoming arrow go to second. So that's a rule. So then we have this kind of convention. Once we draw this space-time triangulation with the arrow, then we have this path integral. But we want to make things even more general. That is, naturally, because we have time direction, you can say all the arrow pointing one direction. That's very natural. But we say, why we do that? Let's allow arrow to point in different directions, so we can even allow arrow to flip. And so then we're still using the same rule. But if you allow arrow to flip, then the notion of then here in this for this segment, this should go to first, this should go to second. And that's different from the other convention, because the other convention, this go to first, then this go to second. So they kind of, in time direction, things get flipped. And then we can flip back. We say, whenever we have an arrow pointing in the wrong direction, then for this element, we're still using the convention that the index with no incoming arrow go to first, index with one incoming arrow go to second. But because this arrow is flipped, the whole element have this complex conjugate. So that's a convention. So once you do this convention, we see that this path integral, even with a flipped arrow, would produce desired results. Because the exchange of these two index and taking this complex conjugate cancel each other, because this is a Hermitian this is a Hermitian matrix. Yeah, this is a Hermitian matrix. And so actually this really build up the connection, how to write down the general path integral in physics, in discrete space-time. So to summarize that, first we can triangulate the space-time. And in this particular case, triangulation one-dimensional space as making all the segments. And then we have to put the arrows on the edge. So here we put an arrow on the edge. And then we can for each cell with arrow, we associate that with a tensor. So this tensor basically is a matrix element of this tiny evolution. We put the tensor to this cell. And when the cell has wrong orientation, we should take a complex conjugate of the tensor. So this is basically the rule which is used to construct path integral in the space-time lattice. And now we can forget about this Hamiltonian and say the choice of this tensor is the choice of like a Lagrangian or Hamiltonian. We can pick any tensor we want. Then different tensor would describe a different quantum system. And so strictly speaking, we describe a general way to construct the path integral in a space-time lattice. And so this is a recipe. And for each choice of tensor, which give us different theory. So this is like a tensor network description of a path integral. And so certainly this can be generalized to higher dimension. So let's describe this generalization in 1 plus 1 dimension. So what is a path integral in 1 plus dimension? Then here we triangulate the space-time. So this space-time is triangle. Okay. Then we put arrow on the edge. But to put arrow on the edge, there's a rule here. It's not you can see around each triangle, they are frustrated. So you have say there's 2 arrows in the same direction, but the third arrow always in the opposite direction. So there's no triangle where arrow form a loop. So that is not allowed. So this is a convention. And so once we put in this kind of arrow, that's we call a branching structure. So this is very, very important. And actually, we didn't realize this before. With Zheng Chen, we wrote a paper on fermionic topological order. I forgot what time, maybe in 2009, 4 years ago. But that time, we didn't realize this. And later, we realized we have to add its branching structure. So we have to modify that paper. But fortunately, that paper is not submitted even 4 years later. So we still have a chance to modify that paper. And so the branching structure is very important to define the fermionic path integral, but also important to define even bosonic path integral. Okay. And then for every triangle with a branching structure, we just add this tensor. Okay. But whether this tensor is we don't have this subscript, just this tensor. But whether this tensor enter as a complex conjugate depends on whether this triangle have a plus or negative orientation. But this plus or minus orientation depends on there's dominant direction. So this is the dominant direction. If a dominant direction point inside inwards, then that's a negative orientation. And here the dominant direction is like going this way, anti-clockwise. So it's a point outwards. So that's a positive orientation. So therefore, for this triangle, this nu enter just as a nu. But for this triangle, nu enter as a nu star. And so this way, well, we define a path integral. So therefore, our path integral, our theory actually is really just described by choosing different tensor. Then we get a different theory. It's like by choosing different Lagrangian. And this, so in this case, the index of tensor happen to be here in this case we choose as a group element, which live on the vertex. So on every vertex we have a group element. Then for each triangle we have the tensor which depends on these three group elements on these three vertex. And so this way we construct a generic tensor equal. So next question is that how to choose this tensor, this function, mu, the gi, g, g, k, how to choose this new function such that it corresponds to a fixed point action amplitude. And it corresponds to this kind of topological term, or whether there is a topological term or not. Just became how to choose this tensor. Okay, so any question here? Yeah.
So do you have to sum over all different kinds of triangulation, or just the one of them?
That's a very, very good question. And I'm not doing quantum gravity here. So I don't sum over triangulation. And however, remember that every theory can be put on the curved space, and you can sum over different metric. Then you get a gravity theory. And here, the real question is to that. So the theory on the space-time lattice can be promoted into the gravity theory by summing over all different triangulation. And but here we do not do that. If we do not do that, that means we have a fixed background space-time. So we are still doing condensed matter physics rather than quantum gravity. But there is a way to promote this formulation to quantum gravity. Okay. And yeah. And then here, since we have a symmetry, because we remember we are describing a nonlinear signal that have a symmetry. And if you want to have a symmetry, then this kind of a tensor, which basically this tensor is like a Lagrangian. It's not arbitrary. We should have certain property. So they have this tensor should have this property. If this tensor have this property, then this tensor describe a theory with a symmetry. The symmetry group is a G. Okay, so that's this is a symmetry condition.
Sorry, a naive question. So why will we choose a triangular lattice to do this space-time 1 plus 1 dimension rather than square lattice? It's a naive question.
When you have square lattice, you can make them into triangle lattice. Each square is a two triangle. So therefore, in the square lattice, you're just using two triangle. This is a square lattice, because this is square.
I understand.
Yeah, so this is actually, when you put the two triangles together, using the product of these two new on here and here, you get a square lattice formulation.
So is there any particular strategy, advantage here? I'm just curious.
So this distinction may be technical, it's not crucial.
Okay.
And so basically I'm using triangle because I'm using this standard triangulation in mathematics. Now, in the triangulation, this simplex have a fixed choice. In two-dimensional simplex, always triangle, three-dimensional always tetrahedral, etc. So there's I just using this canonical choice, and so they are not crucial. You can use other things. This should be fine. And maybe since you raised this question, maybe I want to say that the symmetry we consider here are this internal symmetry. We do not have a space-time point group symmetry. When you want to implement a point group symmetry, then the choice of the triangulation should should have a more constraint. Like if you want to study this like a 90-degree rotation symmetry, maybe choosing the square will be more reasonable. And but here we don't do that, so we can do this. This makes things simpler. And so right now, then we try to say that we try to choose some kind of new so that it gives rise to a pure topological term. So we just want to choose this tensor to construct pure topological term. And the choice is very simple. If you just choose mu equal to 1, that's pure topological term. because the pure topological term means have this defining property is that on every pass, the total action amplitude equal to 1. So remember that's our definition of a pure topological term. That's for every pass, the action amplitude equal to 1. Then the sum over different paths means sum over different 1. They're all constructive. Okay. So to find a nu which describes a pure topological term means to find a nu that is action amplitude for every choice of path, for every choice of G, all equal to 1. And this choice is very easy to make, is that just make nu equal to 1, then this product also equal to 1, and that's it. So actually nu equal to 1 is indeed a fixed point action. So that's one of fixed point action. But it turns out to be nu equal to 1 is a trivial fixed point action. Okay. So therefore, to find something non-trivial fixed point action is correspond to, do we have some other choice of a nu such that the product is still always equal to 1. But always equal to 1, here I want to say that always equal to 1 on any sphere or on any closed manifold. But maybe let's be fixed, or to be something definite. It's always equal to 1 on any sphere. If space-time is a sphere, then the action amplitude equal to 1. Okay, so let's fix that. Assuming space-time is sphere, we want to find some non-trivial choice of a function such that this product always equal to 1 on any sphere. Okay. And so here we make some kind of assumption, which is nu always equal to always a pure face. And so let's assume this assumption. I don't know why I should. If nu is not equal to pure face, I think things let me see. It should flow to pure face, but I don't know how to argue. On the RG flow, the nu should be flow to pure face. So let's don't argue that. Or maybe let me put this way. I can argue that, but I don't know how to show that. Remember when we do the RG in the field theory, we say lambda in a large lambda phase, lambda would flow to infinity. And remember, this term is a real part of the action, and topological term is the imaginary part. And the real part, lambda flow to infinity means real part is always equal to 0. And this kind of picture corresponds to this nu always equal to pure Yuan phase. So there is no dynamic or real part, and only pure barrier phase part. That means nu always pure Yuan phase. So that's motivation why we assume this. Although I cannot prove it, but we have some motivation or intuition to say why this should be true. Okay. And then after assuming nu is a pure Yuan phase, and assuming nu have this symmetry condition, then this condition that the action amplitude equal to 1 on any sphere can be led to this result, because the simplest sphere is tetrahedron. You know, tetrahedron is the simplest two sphere. It have a 4x4 triangles, so that's the simplest two sphere. So therefore, on the tetrahedron, we can see that the action amplitude for each tetrahedron is given by this product of 4 nu, and each nu is associated with a triangle. And this should be equal to 1. So that's a condition that this nu describe a topological term is that this condition equal to 1. So let me describe this a little bit. So let's look at the G1, G2, G3, this function. Okay, this term. This term corresponds to this triangle. G1, G2, G3. Okay. The first element G1, like look here. G1 have no incoming edge. Both edge is outgoing edge. So no incoming edge go to first variable. G2 have one incoming edge, one outgoing edge. When you have one incoming edge, this element go to the second. Then G3 have two incoming edge, no outgoing edge. So two incoming edge go to the third. So therefore, when you once have branching structure, the vertex on every triangle are naturally ordered. They have natural order. Then this using this natural order, we know which index go to first, second, or third. Okay. Then using this, you can also see that This dominant derivation